Okay, so let's draw the shear moment diagram for this problem. First thing I'll do is find some reactions. And you can see here I have looks like a rocker roller support. So I'll come over here and draw, I'll just call that point A, so I'll have the shear at A. And then I have a pin at B, and I'll come over here and draw a positive shear at B. So the first thing I want to do is find those reactions. Now along the way, as I sum moments to find the reactions, I'm going to want to deal with a concentrated equivalent version of this distributed load. So the area under this curve is 4 meters times 4 kilonewtons per meter, so that'll be 16 kilonewtons. And let's say I'm going to sum moments about A. The distance to that centroid is, well, it's half of this is 2, and then 2 more, so 4 meters. So that should be enough for me to do the statics. So I'll first start by summing moments at A and make sure it's in equilibrium. So all these forces applied to the beam create what kind of moment about A? Positive or negative? Negative. So I'll just start from the left and work my way over. So I'll start with 8 kilonewtons, and it has a moment arm of 1 meter. Then I'll have my concentrated equivalent force, negative 16 kilonewtons. And we've already determined its moment arm, 4 meters. And then minus 4 kilonewtons. And its moment arm is, let's see, 2, 4, 5. And then I have the shear at B, which also creates negative moment. And it has a moment arm of 6. So we should be able to solve for the shear at B. I think it's going to be negative. You're going to need to help me with this. 15.3. Anybody else get that? What's that?
It's not supposed to be the 4 kilonewtons, not supposed to be 6 meters, and the shear B is supposed to be 8.
No, it's. Oh wait, you're right. So that's 2, 4,
5,
6. Wait. 2, 6, 8. This should be 8, and this should be. This should be 7.
7.
Messed that up big time. Okay, so Mr. Church, you'll have to recalculate. Sorry about that.
Negative 12.5.
Oh, that sounds nicer. Anybody else get that? Okay, cool. Thank you, Mr. Randolph.
I do my best. I should get an A for effort.
If I gave grades for effort, everyone would get an A. But I don't do that. Okay. All right, so let's sum forces in the y direction. I got my shear force at A acting up. I've got my shear force at B acting down. And then all these other forces are down. So I've got minus 8 kilonewtons, minus 16 kilonewtons, and minus 4 kilonewtons. Now remember, the shear at B is also negative, so what's my shear at A?
40.5.
Really? This is negative, so it comes in here and becomes a positive.
Sorry.
This is 28 minus that, right?
15.5.
15.5?
Yes.
Okay. Go ahead. What was it?
Is your B of A going to equal your A of Y?
I don't care about A of Y. I care about the shear. I'm drawing a shear diagram, right? So this is positive shear at A. This is positive shear at B. And when I just solved for my shear at A, I got a positive value. So that means I start off with a shear of positive 15.5, and I end with the shear of negative 12.5. So I know the boundary of my shear diagram. So let's draw the left and right edge of the beam. I'm also going to have this point of interest at underneath each of the loads. And then something's going to probably happen here too, so I'll include that. So my template is going to get kind of crowded. Let's see what we get. So here's positive X, positive shear, and we're going to do all of our forces in kilonewtons. So the shear at A is 15.5 positive. The shear at B is negative 12.5. So we got to see if we can make all that fit. Now we remember our basic principles are that the change in shear is the area under the load diagram. So let's start and work our way over. So starting here over the first meter, what's the area under the load diagram? It is 0. So there's no change. And we know the shape because we know that the slope of the shear diagram is equal to the load, right? Those are our two basic relationships. And what is our load over the first meter? 0. So we have 0 slope. So we have constant shear. Now what happens as we go from the left side to the right side? How much does our shear change? It changes the value of the force, which is 8, and that's negative. So we go minus 8, which would be, what is that? 7.5? Let me write that right here. The change in shear over the next meter is the area in the load diagram. The area in the load diagram is 0. So it stays 7.5. The slope of that curve is equal to the load, and the load is 0, so we have 0 slope. So it just steps down. Now what happens over the next 4 meters? Well, the change in shear is the area in the load diagram. Here's the load. It's a rectangle. And the area under that is, same as our concentrated equivalent force, it's negative 16. So 7.5 minus 16 is 8.5. What's the slope of our curve? It's equal to the load, and the load is constant and negative. So you can see there's a point where it crosses the axis, so that's going to be a new point that we're going to be interested in. And for the time being, I'll just call that X1. We'll come back and get that in a second. Let's go ahead and finish this up. So what happens over the next meter? The load is 0, so there's no change. The slope is given by the load. The load is 0, so that's a 0 slope, horizontal line. And then what happens as we go from the left to the right-hand side underneath this 4-kip load? Yeah, the shear changes negative 4. So that should bring us to negative 12.5. And then you can see the last meter, no load. No load means no change. That's great. It matches. And the slope is given by the load. The load is 0, so we get 0 slope. So we get this very strange-looking diagram. We have a constant section, and it changes, and then it steps again. So how do we find this distance x1? Well, let's apply our same forces. So first of all, what is the change in shear from here to here? Well, it starts off at 7.5 and drops to 0, so that's a change of negative 7.5. Simultaneously, what's the area under the load curve? Well, if I project this line up, And I'm now looking at the area under this load curve.
7.5.
What's the area under that rectangle? It'd be base times height. The base is x1, the height is 4. So that would be minus 4 times x1. Well, these two things are equal. So I get an equation that says minus 4 times x1 is equal to minus 7.5. So x1 is equal to 1 point something. What's 7.5 divided by 4?
1.9.
1.9? The negatives cancel. So if that's 1.9, that means this side is 2.1. Right? So this now becomes 1.9. So this side should be 2.1. That's not feet, it's meters. So we have all of our geometry that we need now. So let's see if we can figure this out. So let's start with the x-axis for our diagram, positive moment, and our moment will have the units of kilonewton meters. What's the moment at A?
0.
0. What's the moment at B?
0.
0. So we know we're starting. We need to make these two things connect. Now the process we're going to use is that the change in moment is the area under the shear diagram. So let's start here. First meter. What's the area under the shear diagram?
15.5 kilonewton meter.
It's going to be 15.5 times 1, and that's positive. So I'm going to go up to 15.5.
The meter.
What's the shape of my curve? Well, remember that the slope of the moment diagram is equal to the shear. And the shear is constant and positive. There's a constant positive slope. Everybody see that? Now, what's the change in moment over the next meter? With the area of this curve, which is 7.5 times 1. So I add that to here, and I get, what is that, 23? What's the shape of this curve? It's given by the shear. The shear is positive and constant. It's slightly smaller, so it does dip down a little bit. Now, bless you. What's the change in moment over this next segment, which is 1.9 meters? Will be the area of a triangle. So, what is the area of the triangle? Its height is 7.5, base is 1.9, divided by 2 is, and add that to 23. 30.1. Now what's the slope? What's given by the shear? So I look here, the shear starts off positive and drops to 0. So I know this is a 0 slope and this is a positive slope, so I get this kind of curve. That looks good. So let's continue. So what's the change in moment on the next section is the area of the shear diagram. What's this area? So it's a triangle again. 2.1 times 8.5 divided by 2. So subtract that from 30. What do you get? 21.2. This is not going to be to scale, but you get the idea. 21.2. Now what's my slope? What's going to start off, it's equal to the shear. It's going to start off at 0 and become negative. So there's a negative slope. So it's going to do something like this. Now what's the change in shear, the change in moment over this next meter? Negative 8.5. So subtract 8.5 from that, and what do you get? Do we get 12.5? We're going to be off a little bit, aren't we? What did you get?
12.7.
Somehow we lost something along the way.
Well, the 30.1 is supposed to be like 30.0.
Yeah, I used the actual numbers as opposed to I didn't keep rounding.
30.03.
So this is really 30.
Well,
It's closer to 30.
Okay, so what would this be?
So that'll be
21 point. We're still going to be off a little bit. It's going to be fuzzy. That's okay.
you could just say 30 minus 5.
0.075. Okay. Just 21?
That would be, yeah.
Okay. Let's just make it 21.
Can you just say that?
It's close enough. I'm not going to get too upset if you get to the end and you're off by 0.1. That just means you rounded too soon or too early. That's okay. So let's just finish this part. So what's 21 minus 8.5? It's 12.5, isn't it? And that's going to have a constant slope. And then the last part, the area of the curve, is again 12.5. That brings us to 0. That's close enough. Yeah.
Can you just say x1 is 2 and the other side is...
It's not 2. Since this side is smaller than that side, it is going to be shifted.
Okay, cool.
Now right here, this could have been an error. Maybe it's not exactly 1.9. Maybe it's 1.88 or something. Maybe we should have kept 3 significant figures.
But
I'm not going to get too upset about this if you're off by a little bit.
Concentrated load exactly in the middle.
Yes, it is.
So why wouldn't it be just 2?
Because these loads are not equal. So it's shifted to the right or to the left.
Okay.
It's skewed.
It's skewed. So what's the maximum moment?
30.
30. And where does it occur?
If
If you want to measure from A, it would be 2.9.
It's always, when the shear is 0, the load is always maximum.
Cool.
So any questions about this one?
No.
Okay.